a very thoughtful gesture for Professor de Klerk of the University of Alberta to put together the next talk, which should lead into the dinner presentations very nicely. And a little bit about Professor de Klerk. He actually started out in analytical chemistry at the Forensic Science Laboratory of the South African Police. And then he became the manager of their precious metals analysis group. He became a professional engineer during the time he worked in catalysis research at Sasol, where he worked on refining catalysis and pilot plant design. He became research manager of the FT Refinery Catalysis Group in 2001, where he coordinated both industrial research as well as research with universities. And he moved to Edmonton in 2009. The title of his talk is Advances in the Catalysis of Fischer Tropsch Refining Made Possible by Burt Davis.
Thank you very much. Thank you for the introduction. Okay, so I'm a little bit younger, so I haven't known Burt for 40 years. But due to my youthful appearance, I have a slightly different perception of Burt. And I managed to get this, so since we all deal with Greek, this is actually where you should go and look for the pictures. Dr. Cook managed to get a couple of years, another one with Burt. And, you know, Burt has really been a role model in catalysis for me. So he's far more than just a scientist, in my view. He's a little bit elevated above that. So, he has contributed to many of the types of catalysis that I find interesting. I'm more on the refining side, so I'm not a Fischer Tropsch person myself, but I have to deal with all the stuff that comes from the Fischer Tropsch reactor. I do appreciate Fischer Tropsch catalysis, but as you can see, there's a lot of refining catalysis, so we haven't heard too much about refining catalysis. And hopefully I will change that. In the interest of time, I've agreed, concocted some sort of agreement with our chairman. I will only discuss alcohol dehydration. Now, I know this is very heinous to discuss alcohol dehydration just before a dinner. We should focus on the opposite reaction, olefin hydration, but okay, bear with me for this. So let's have a look at alcohol dehydration. In order to discuss alcohol dehydration, we have to start with history. Again, this is at the insistence of Burt. You know, this is about him. He loves history. So we have to see where we started using alcohol dehydration in the Fischer Tropsch community. And it actually all started here in the US. Alcohol dehydration was used as a commercial process to do double bond isomerization and deoxygenation. And bauxite was used as a catalyst, which is alumina ore. It's used for commercial production of aluminium. And although it's alumina rich, it's not just alumina. It has a couple of other cats and dogs in there. The key thing is this catalyst did the two things. It removed oxygenates, mainly alcohols, and as you know, Fischer Tropsch synthesis is not only a hydrocarbon synthesis, it also synthesizes oxygenates. The other thing is, it isomerized the double bonds. And this was important from a motor octane number perspective because linear alpha olefins have a lower octane number than linear internal olefins if you do motor gasoline, if you produce motor gasoline. Now this was a high temperature Fischer Tropsch process, so most of the product ended up being in the naphtha range, and this was a key technology in the late 1940s, early 1950s to produce a final product. So alcohol dehydration is important in Fischer Tropsch synthesis. We fast forward a little bit. We again encounter alcohol dehydration somewhere else. And it's not only in the US that this was practiced, the previous example, but this was practiced only in South Africa. And when you look at the alcohols that are dissolved in the aqueous phase of the Fischer Tropsch product, what do you do with that? Well, you can sell it as chemicals, you can purify it, but if you're in the fuels business, there's only so many alcohols that you can add in, and there's only so many that the motorists will tolerate. So one of the thoughts was, well, it's quite easy. Maybe actually all we should do with this is just rip the alcohol group out, turn it into alkenes again, and then we can deal with this in the oil refinery. And this was indeed done for a couple of years at the Sasselson Fuels Refinery, also on commercial scale. So alcohol dehydration was again found in a fuels refinery context. Now I want to switch gears from fuels refining to chemicals refining. So in all of these cases, doing double bond isomerization and pushing towards olefins had been a good idea. What if you want to do chemicals? Now, more recently, a process was commercialized by Sasol where they converted 1 heptene to 1 octene. So 1 octene being a high value chemical, 1 heptene potentially high value, but nobody uses it. So, how is this done? First of all, you get hold of the 1 heptene from the Fischer Tropsch syncrude. So this is a fairly complicated extraction. Once you have the pure 1 heptene, you go to hydroformylation. For those of you that have been here earlier today, this is something that Dr. Bell discussed as one of the potential routes of upgrading smaller or shorter chain olefins. In this case, it's a rhodium-based process. You produce the octanol, so the aldehyde, so the oxygen group is the terminal group. You also grow the chain by 1 carbon number. Then you hydrogenate it, and now you have 1 octanol, and now the dehydration is the last step to convert it into 1 octene. So quite a number of steps, but ultimately you convert an olefin from an olefin to an olefin, but you grow the carbon chain by 1 number. Now this is easy dehydration, or at least seemingly so, because if you have 1 octanol and you take out the water, only one thing can happen. The double bond will form in the terminal position, so this is your desired product. For those of you that look at the small peaks on chromatograms and look at the devil in the detail, life is hardly ever as simple as this. The key issue here is that we want to do this reaction, which is very simple. We at all costs want to avoid this reaction because 1 octene is a valuable product, 2 octene is something you put in fuel. So you go from chemical to fuel. So chemical, fuel. Not a good idea. So the business model doesn't work so well. If you remember, we had a fairly complicated process here. So you spend a lot of effort getting to the final step. You definitely don't want to go through all those steps to take fuel to make fuel. Doesn't make any sense. Life is a little bit more complicated, of course, in the real world. So it's not just dehydration. We know that dehydration to 1 octene, there can be side reactions. And if we read some of Burt's work, we know which of these side reactions there are. Now the first one that we have here are ethification, which is a very simple, on its way to dehydration. You can do ethification, but you can also do dehydrogenation. But as engineers, we're not worried about this because we can devise ways within the process to deal with this. So should we have these side reactions, we can just use a recycling to get rid of it. So I'm not going to focus too much on the side reactions. I acknowledge for this point and for the discussion that they are there, and we will only revisit them later when we have to. So let's make things a little bit easier. The side reactions that we are going to worry about today are mainly double bond isomerization. So we didn't want the 1 octene to turn to 2 octene, and there's 2 possible ways that we can conceivably see that this is going to happen during the process. The first is the tried and tested acid base. I mean, let's face it, when we see double bond isomerization, the first culprit we are looking for when we call the police is there's branched-in acidity. You know, there has to be branched-in acidity. You know, if somebody lies bleeding on the floor with a knife sticking out of them, well, you know, there had to be a murder. Couldn't be an accident. You know, or watch too much TV. But there's also the hydration-dehydration interaction. And that is something that we should not forget about. So these are both isomerized inside reactions, and we have to minimize them by a clever combination of catalysis and reaction engineering design. So not just one, we have to look at both. So let's ask Burt to look into this for us. I mean, this is after all about him. And he's the guy. He got the prize, so let him solve this issue for us. We want to improve this process. So what did Burt do? Well, Burt studied alcohol dehydration a lot. And unlike me, who was a little bit of a wimp, he studied 2-octanol dehydration, not 1. Now this is a bit more complicated because the 1-octanol goes only one place. 2-octanol can go many places. So 2-octanol can be dehydrated to either cis or trans 2-octene or 1-octene, depending on which way the catalyst works. So what did we learn? What can we learn from the literature that he has created basically around about the time I was born? Slightly after. So the first thing that he tells us is that, yes, if there's any of the usual suspects in the catalyst that causes traditional acid-base type of double bond isomerization, these sites are usually rather quickly deactivated with time on stream. So for commercial operation, yes, during startup this might be an issue. For longer time on stream, they'll typically be killed. Some work that some of my colleagues did, Boulder and Mulder, published in Applied Catalysis A, actually confirms this. So they've shown the moment you have other oxygenates present, typical Fischer Tropsch stream, with time on stream fairly quickly for ether alumina catalyst, end of the road for double bond isomerization. Well, there's also the question of competitive adsorption. So what Burt found is that if you have alkenes in the presence of alcohols, there is competitive adsorption. And so as long as the alkene content is low enough, hey, who's the boss? The oxygenates. They are far more effective at competitive adsorption on a polar surface than the comparatively less polar olefins. So the alkenes do not effectively compete with alcohols in a mixture. So even if you're worried that there is some double bond isomerization, acid catalyzed double bond isomerization going on, one way to deal with this is just keep the concentration of the olefins low. So as engineers, we know how to do this. Hey, we like to do paraffin dehydrogenation to make alkenes. What do? We keep the pass conversion low. Even in Fischer Tropsch synthesis, we're afraid that the catalyst is going to deactivate by water or whatever other means. We keep the pass conversion low. So this is an old trick. So nothing new about this. And Burt tells us, well, nothing is going to happen as long as you keep the pass conversion low. The other interesting thing that he found over alumina, and let me first acknowledge, alumina is one of the most humbling catalysts I've ever come across, is that when you dehydrate 2 alcohols over alumina, the primary products are a 1-to-1, in a 1-to-1 ratio, the cis 2 octene and the 1-octene. Wait a minute. You think back to your organic chemistry. Isn't this supposed to be Zaitsev elimination? Aren't we supposed to almost exclusively get 2 octenes here? And by the way, isn't the trans isomer the more stable one of the two? Well, Burt tells us this is what we get. So this is puzzling. Well, he did not only study alumina. He was a very productive soul. I mean, you can see he's lost a couple of hairs doing all this metal oxide catalysis work. So he's actually looked at a lot of the metal oxides. And there's some general trends that can be deduced from the work that he has done. One thing is that the selectivity and the activity of the metal oxides are hugely dependent on the feed pretreatment. For those of you that have played with metal oxides,